tensor field visualization, we will look at technique focus on texture-based approaches. In particular, we'll first focus on the generalization of the line integral convolution approach, in this case called hyperlick, where the original idea of integrating along a particular direction of a vector, the way would be on vector field, and then creating a stencil for integration that takes the noise image and computes an integral that gives a result to a particular pixel. This concept of integration along a line that apply to vector fields need to be generalized to the case of tensor field, where the one-dimensional integral that would be discretized into a single summation is replaced by a double nested summation, and of course the following computation in evolution over time. The idea behind it is the fact that we would sample on the vertices of the grid, the image, the tensor field, so that we can compute our square stencil and rotate them along the directions of the eigenvectors, and then stretch them based on the eigenvalues so that we have rectangles in the various directions that represent better the information regarding the diffusion in multiple dimensions of the flow represented by the tensor field. And so this allows to replace the linear stencil of integration with a deformed, if you will, rectangular structure, which is regularly still based on a grid with a couple of a main dominating direction and a set of secondary direction. And this became kind of the basis for the integration and the summation in the double nested form. So here, then now this formula with the discretized integral will start making sense. We would replace this single linear representation with kind of the rectangular structure that we saw before, with a kind of logical representation as a grid, although it's mapped as a deformed shape on the stencil image. And that would follow this particular summation, the integral that gets discretized to give rise of the value at the end in the destination texture. So intuitively, this will give results that are somewhat similar to the lick images, but in a way they're less directional, less crisp, exactly because they will show, in this case, for example, both the radial direction of the flow as well as what degree of transversal flow may happen in the particular model. This is, I guess, more intuitive if we look at that in animation. And so this is what those images show, where we see, in the case on the right, a very strong radial flow, while in the image on the left, we see a much stronger component of the rotational flow, obviously in addition to the radial component. You see how when we evolve, we can see both direction of the movement, and this kind of give this kind of a little bit blurry direction, but it's not because the image is low quality. Is effectively representing a certain characteristic of the data that were being visualized. Here it's a case for a medical data set. We saw during the movement kind of the flow in this particular region and how that evolves over time. And so here we can see that kind of more directly. Here the flow is kind of not very strong, so I hope this is visible in the image of the video. probably not if you're watching this kind of on a phone or something really small. In the 3D, we can use this as a basis of having a geometry embedded in three-dimensional space and show the direction and flow along the different tracks. And this is better visualized if we have full illumination and better rendering. And so here you see the shape of the tracks is kind of U-shape, and then how they evolve inside the brain. And finally, how this come together with a full visualization of the entire brain structure, and how that kind of you see here the separation between the two parts of the brain, how they're connected together from the fiber structure, and of course it will require a medical expert to do then the fine interpretation of what that really means in terms of the flow inside the brain. As any texture-based approach, this can be applied obviously not just in 2D or in 3D, but also in 2D surfaces embedded in 3D. And here we can see how the flow in areas that are more isotropic, it becomes kind of less pronounced. When instead we have a strong directional component, we have a flow that is represented in a way that is much more similar to a vector field representation. Now, to accelerate the computation, this can be also achieved with two independent computation in the direction of the primary and secondary vectors, eigenvectors of the flow, and then weaving together the results so that with this type of pattern, so that we can see both the primary and secondary direction. So this has application to limited cases, but can be very effective in practice. Now this gave rise to a very similar representation in 2D, but then generalizes much better in 3D with this concept of the hyper streamlines. Effectively, we will look at computing streamlines in one of the directions, and then look at the second order and represent them transversally to give the representation of both directions for proper visual representation. And so here we can see kind of in red one of the direction, and in green the other the directions, and how they nicely weave together. And in this case we have a full representation. Again, here in red we have the major eigenvector and the flow in the direction, and in green kind of the minor one. And we can see how drawing those together give the indication of the flow in all the direction, the one that is stronger and one that is not as strong. What's interesting is that this approach can be generalized in an interesting way in 3 dimensions, where we continue to use the concept of streamlines. So taking the main eigenvector and build a kind of elongated structure like this. But then those are cylindrical in nature, and then the transversal information in the cylinder can be computed by the other eigenvector. And so, as indicated, so main direction of the streamline kind of in a traditional way. In a way, it's similar to what we would call a stream tube. But then using the other eigenvectors to modulate their shape along the flow and highlight how that would change over time. And so the minor eigenvectors, if they're equal in magnitude, still give just a circular cross-section, so the hyperstreamlines become more of a cylinder. If the two are not equal, in fact one is much larger than the other, we have this ellipsoid structure, and then the tube become kind of squished in one direction, so that one can appreciate the direction of the flow in one way or the other. Those are results of applying these techniques in full 3 dimensions. And here you see the representation of the hyper streamlines in the tracks of the brain. So again, those are the main direction of the flow, but then the structure of the tube is influenced by the second and the third eigenvector in the data, so that one can understand if the main direction is dominant and how much the other two kind of work independently. Some of the potential weak points of the hyper streamlines is that in the region where the flow is more isotropic, we don't have the strong distinction of the eigenvectors between each other. In fact, we have the problem that the computation of the eigenvector kind of become somewhat random. Let me go back to the previous slide. When the two eigenvectors are really the same, one end up with a circular structures, and effectively you can have any two vectors in this basis would be appropriate results of the computation. So that makes the computation kind of unstable, and so the hyper streamline can kind of start wandering around because it does not have a strong basis to choose one direction over another. This concept of tensor line has been developed to compensate for this effect, where if in a certain region that is isotropic, the flow comes in a certain direction, the computation tend to maintain the flow around the same direction, so that we don't have these artifacts of kind of randomly evolving flow in the data, but it tends to continue along the choice that was selected at the beginning as the input. And so this is kind of the main advantages of this approach. So the computation takes into account the input of the vector coming in, the velocity, so that the result is stabilized when there is no real preferential direction, and there is a tendency of combining things and continue the flow linearly in the direction that it came from. So this is examples of tensor lines, and in particular we see the tensor lines following these directions in yellow, while the cyan one are the hyper streamlines that, again, in regions where we have less isotropic flow, they tend to kind of wander in a kind of random way. Addition of the work in hyper streamline representation is that the transversal direction of the flow can be represented also by different glyphs. Here we see this particular shapes where, so the hyper streamline is effectively a uniform cylinder, but then the various shape can give the additional information regarding the evolution of the tensor. In building this type of representation, it's important to see what we can do best to interpolate the glyphs themselves. So, for example, if we have this three models at the corners of this triangle, and we want to compute all the direction of the glyphs interpolated in the triangle itself, there are different ways of doing the interpolation. On the left, we see the linear interpolation. And as you can notice, this is not very expressive of how the flow is actually turning as an angle, but things kind of become more of a circular structure with no preferential direction, and then they become an ellipsis again. With a better way of doing the interpolation, we can actually get the glyphs to follow to maintain the shape instead of being deformed and kind of squished again, to maintain their shape and then follow just the rotation of the angle. Maybe it's important to highlight that the glyphs at the corners of the triangle, they're all three kind of thin and elongated along a direction. And so it's more intuitive to think of them as rotating, as in the interpolation on the right, instead of becoming anisotropic as we see kind of in the middle, and then be isotropic again on the right. And so those are typical interpolation challenges that happens a lot when we deal with rotational structures. And in this case, with the glyphs, it become really evident how if I interpolating between one cylinder to another, instead of going through a flat kind of parallelepiped shape, it's better what we see at the bottom, that we're looking at a cylinder that gets elongated properly, rotated, but does not go through interpolation in between. The worst is the linear case, where the shape is deformed and then recorrected at the end. That it just defies the intuition of the user. Now, to conclude, I want to show some images out of a video. This also is a video that is going to be available on the web. So here we see how these classes of visualization are used for data acquired from DTI, diffusion tensor imaging for brain data. And the main direction of the eigenvector give rise to this Y matter tracts. And those can be pre-computed in large numbers, but then they can be used for this type of interaction based on the concept of putting probes in the space and figuring out what flows connect to particular locations. So even if the overall picture is kind of very busy and hard to work with, the introduction of a proper probing mechanism, so this red region is kind of the probe that one would put as part of an interactive system. And so a scientist can look at how two regions can be connected with each other, how interactively they can select one bundle, see how it's related. For example, is this region connected only to the bottom one or to different location there? The discovery of all those connections can help the user, in this case a doctor, build a proper mental picture how the different parts of the brain are connected with each other, and how they work kind of in a healthy way or in a pathological way. And so this conclude this discussion of visualization with tensor imaging, and next week we will move forward with a new topic. Thank you.